Hello, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 23 in the series, Graphing Relations and Functions. So in this video, we're going to go a little bit more deeply into the graphs of relations and functions. We're going to be principally concerned with two main things, which is number one, analyzing the graph to discern domain, range, and whether or not a relation is in fact a function from the graph alone. And then we're also going to want to see how to evaluate functions and relations for given values just using the graph. Now, relations are very general objects, and as such, their depictions can be strange and wonderful. We are going to be primarily concerned with graphs, which are also curves. Now, in mathematics, we can think of a curve as being the path through space that a point would trace out. So if you imagined a point hanging out in space and then you moved it along, it would have a history of where it had been, where it was going, and this history would be a curve. Now, this also includes lines. Lines aren't very curvy, yes, but in a mathematical sense, a line is a curve, right? A line is a trajectory of a point. So we could think of it as a curve. Now, how does that relate to a graph? So the graph of any relation is the collection of all ordered pairs, x comma y, where y was the value that was assigned to x by the relation. So remember I said it wasn't that bad of a notation abuse. This is why. Because we are going to plot those points as coordinate pairs. And even though we can define relations that have absolutely insane graphs, what we will see is that if we define a relation through an equation, that very frequently, in fact, for all the equations we're going to be looking at, the graphs corresponding to those relations are in fact curves. Here I have drawn some curves. As you can see, they're a wacky and varied bunch. They can do all sorts of things. They can shoot off in a direction and keep on going. They could be lines. They could start and stop. They could connect back to themselves. They could spiral inward forever, right? So what we are going to look at in this class is only a small set of possible curves. But here's some things you should keep in mind about how curves can behave. So some curves are finite. They start and they stop. Maybe I include the endpoints, or maybe I exclude the endpoints with the usual interval kind of dots to them, right? So actually this might start here, but not exactly there, just past it. Here, this ends precisely at this point. Now, some curves don't stop. Some curves go on forever, and we use arrow notation to sort of indicate that that is the case. Sometimes it's left for you to figure out, but most of the time, if we're going to say that a curve keeps on going, then we put some arrows on the end. Now, these are especially tricky because you have to sort of use your imagination and maybe a little bit of knowledge about math lore in order to know how those curves are going to behave once they leave the page, once we no longer see them and they just keep on going. So think of a line, right? A line technically extends forever. A line is this idealization of straight line movement in reality. It goes on and on and on and on. It doesn't ever stop. So lines are very much like this. Another very common piece of math lore that you'll need to keep on deck is the behavior of parabolas. So parabolas come up when we talk about squares and square roots. We'll talk about these explicitly a lot more in subsequent chapters, but for right now, just about their graphs, there'll be a lot of examples that have parabolas in them. And what you should know is that they get steeper and steeper. They're not like lines. They change slope and get steeper and steeper, or this one kind of shallows out and gets shallower and shallower, but they do widen forever, right? They will get arbitrarily wide. So that's important when we go to look at domain and range later, but for right now, they have this kind of U shape, and you should know that they always get wider and wider, even though they are getting steeper and steeper. A little terminology will help. Let's talk about the domain and range of a relation. Remember that domain refers to all of the x values that get used, and we must assign a value to every point in the domain, and that range are all the y values that are going to get hit, values that are assigned a particular x. So get used or get hit or anything like that really just means that the curve is going to have some point x comma y in it, or your graph of the relation will have some point x comma y on it. So let's look at an example. Before I make some comments here, let's just kind of break this down. We have this curve in red. It dips down, it comes back up, it stops right here. So this is a finite curve. And what we notice is that it doesn't include this point. It dips down, it comes back up, and then it stops here and it includes this point. So this curve has a domain. The x values that are used start at -2 and go up to +2, and it excludes -2 and includes +2. So this would be the domain of this. Remember, when you think domain, think x values. And then the range, so what are the y values? This isn't the lowest y value. It dips down and stops right around here, which I've marked -1. And then it goes up as high as this one here, which I've marked 3. So this goes between -1 and 3. Notice I've included that -1. Let's talk about that. I didn't include this 2 because this x value isn't actually used. I did include this -1 because we generally, if a function looks like it attains like a peak or a valley like this, we will say that it does actually hit the point that it looks like it hit, right? So it really should attain -1 here. -1 is a value that should actually be hit at this point. So we assume for peaks and valleys that they actually hit their targets, and that's why we're going to include -1. Let's look at another nice example. Here is an equation defining this relation. Right? This is a relationship between x and y, and it's phrased that the sum of their squares is equal to 1. It turns out that actually defines the circle at the origin. We can talk about that more later, but for right now, you can take it for granted. And what x and y values are hit? Looking down at the x-axis, it goes between -1 and 1, and it actually does hit those values, so we use brackets. And the range goes the same way. The range goes from -1 to 1, and it does hit those values, so we use brackets. Here's one where I'll dive a little bit deeper into the parabola as an example. So for this one, I have chosen x squared, the simplest parabola. And I've plugged some values in to get a nice shape to this graph. Notice it gets steeper and steeper. Here it goes from 0 to 1, and then it jumps all the way up to 4, right? And then all the way up to 9 at 3. So it keeps on getting more and more steep, but there are no points that I couldn't square. I could square 1,000,000 if I wanted to. So we'll always have this function get wider and wider, even as it gets steeper. And what that means is that the domain is -infinity to +infinity. There is no maximum width of the parabola. The whole real number line is going to get plugged in, so the whole real number line is the domain. Now the range, on the other hand, the range is not the whole y-axis. It never gets lower than 0. It attains 0 at 0. 0 squared is 0, but it never gets lower than that. And so what we wind up with is a range that goes from a lowest value of 0, inclusively, up to a highest value of infinity. So here's some critical notes. I want you to copy this as proof that you watched the video. These are the two most important concepts so far, the domain and range of a relation or function. So recall that a relation is not a function if there is an x value in its domain which is mapped to at least 2 outputs, y. That would still be a relation, but it's not a function. And it only needs to fail at 1 point. Now, what we saw in the previous video is what that looks like for tables and ordered pairs and arrow maps and graphs of points. What we're going to see now is how that would look for curves. Here's a graph of a curve that is a relation but not a function. Notice that at this particular value, x, there are 2 values of y assigned. It gets mapped to this y, which I'm going to call y1, and this y, which I'm calling y2. Both of those are outputs of the relation R. Normally, we don't even use this kind of function notation here because, what would you really, which one do you send it to, y1 or y2, right? But suffice it to say, we would draw these graphs pretty frequently, even if we don't say, R of x very frequently. So, but what is it? What do we see? We see there's a vertical line that passes through this x, and it hits the curve in 2 places. This was analogous to that vertical stacking of points in the last video. And this gives us a nice test to see if the graph of a relation is a function. These are critical notes as well. I want you to copy this. This is the so-called vertical line test. The vertical line test says if every vertical line hits your curve in only one spot, then it's a function. But if even a single vertical line hits your curve in 2 or more places, it is not a function. All right, let's talk about one more idea here, which is evaluating a function. If a function is given in terms of rules and instructions, then you can evaluate it by plugging in values. Like, for example, when we had 3x plus 1, if I wanted to evaluate this at 3, I just change x to a 3 and do my arithmetic, and bada boom, bada bing, I get a 10. But that's not what might happen with a graph. What if we're not given the rules? What if we're only given the graph? Well, then we can still evaluate this and more by looking at the graph. So here's an example. Here I've drawn a graph of a function in green, and I'm saying, what is its value at 2? To figure this out, you go to x is 2 on the x-axis, and you look up to find the corresponding point on the function. Then you go over from that to read its value on the y-axis, and it's a 4. So we would say that the function has a value of 4 when its input is 2, or that f of 2 is 4. Likewise, we can also ask questions about what x values produce certain y values. One of the most common questions to ask is when is a function equal to 0, because 0 are particularly special values. So for this particular function, where is it 0? Well, my x value of -1 has a y value of 0 for the blue curve, and my x value of 3 has a y value of 0 for the blue curve. So we would say that the function has a value of 0 at x is -1 and x is 3. All right, time for your praxis. Is this a function? Consider this graph over here on the left-hand side. This is a relation. It's a curve. But is it a function? Yes or no? What's its domain and range? Evaluate this thing for me at -1 and tell me at what values of x does the relation have an assigned value of 0. Pause the video at this time, give that a shot, and we'll see how you did. Okay, let's see how it went. So is this a function? No, it is not a function. The vertical line test says no. It is a relation. What is its domain and range? Okay, so what are the x values that get used? All those get used, and that endpoint there. So we do assume that it actually hits this point. So what is this blue interval? What is the domain? The domain is from -1 up to 3, and inclusively. Now let's figure out the range in the same way, asking the same questions about y. What is that interval? What's the yellow interval on the y number line? It's our range, right? And that's going to be from -2 all the way up to a highest value of 1 and inclusively. Let's evaluate this relation at -1. Evaluating means what is the value of the graph in its y position when my x value is -1. That's what it means when we say evaluate here. So what is that? Well, when x is -1, my point here is at 0. So the relation is 0 when x is -1. You know, this right here is the point. Now, what about 4? It says, at what x value does the relation assign a value of 0? Values. At what values does it assign, the relation assign a value of 0 to x? So, okay, well, we saw one of them right here, right? That's assigning a value of 0. So this is going to be one of them. This would have been, but it's open. So actually 0 doesn't get sent to 0, it gets sent to +1 and -2, but this one surely does. This one gets sent to 0. So the 2 points which get sent to 0 are -1 and +3. All right, that's it for now. Thank you for your patience. Good luck with your studies, and I'll see you in the next video.